This is question 2 of fifth book, Radioactivity, Deutime number 1. It starts with a comparison of different types of radiation. The question asks us to tick the boxes for the correct type of radiation for each property. So for largest mass, we should remember that alpha particles are formed of 2 protons and 2 neutrons bound up in this alpha particle. Beta particles are electrons, whereas gamma rays are a form of electromagnetic radiation. So alpha particles have the largest mass. The most penetrating, this means the ones that have the greatest range. So while alpha particles might only travel 5 centimeters in air, beta particles maybe around 1 meter, but gamma rays, their range is pretty much infinite in air, certainly several kilometers, so we'll choose those. The highest speed, all 3 travel quickly, but our gamma rays travel at the speed of light, and we know nothing travels faster than the speed of light. For negatively charged, again, once we know the constituents of these things, we can work out the charge. So our alpha particles contain 2 protons, so they are positive. Gamma rays are electromagnetic radiation, so they're neutral, whereas our beta particles contain an electron, or they are a fast-moving electron, so they are the negatively charged one. The symbol for the structure of an alpha particle is 4,2 alpha. State the number of neutrons and the number of protons in the alpha particle. So the idea here is we have at the top our mass number, which is the number of protons plus the number of neutrons, and down at the bottom we have our proton number. We tend to call it a proton number in physics, but equally could be called an atomic number, which is just the number of protons. So to find the number of neutrons, we take the bottom number from the top number. To find the number of protons, we just look at the bottom number. Suggest why alpha radiation is more ionizing than beta or gamma radiation. There are 2 possible options we can go down here. Option 1, to do with the mass of an alpha particle is approximately 10,000 times the mass of a beta particle, infinitely bigger than the mass of gamma radiation, which of course isn't a particle at all. Option 2 is the charge. The charge of an alpha particle is twice the size of the charge of a beta particle, and again, gamma radiation is uncharged. So either one of the 2, it's only for 1 mark, this particular section. C, a smoke alarm contains a source of alpha particles and a detector. The alpha particles reach the detector through a sample of air from the room. The alarm sounds if there is a sudden drop in the detector reading. The graph shows changes in the detector reading. Why is the detector reading never 0? So the idea that we should always have in our head during questions about radioactivity is the idea of background radiation. Here we mean there will be some radiation from the surroundings, mostly natural, small amount man-made, but mostly natural, from the building materials the house has been made out of, from radon gas in the air, from the sun, from other space objects, but there'll always be some radiation being detected. So it's referring to this section down here at the bottom. Why is the detector reading never constant? We have our two words we like to use for radiation, that it's spontaneous and random. In this particular case, it's the random nature of radioactive decay that's important. Part 2, suggest why fewer alpha particles reach the detector if there is a fire. So this again is back to our ideas about alpha radiations and their ability to penetrate through things. The smoke particles are likely to absorb the alpha particles, we might say. We might say the alpha particles ionize the smoke particles. We might say the alpha particles are stopped or scattered, and therefore fewer are going to reach the detector because of the fire. So this idea that the alpha particles are absorbed by the smoke particles is important. It doesn't talk about smoke in the question, so that's why there's a mark to do with the smoke.